There we go. Okay, so as I said, one of the things that was mentioned is likely to be on the exam is the calculation of Pearson's correlation coefficient, or R. And we're starting with this formula. R is equal to 1 over n, and the summation of what are these standardized, these basically sum of squares, I guess, is basically what these are for, what sums are the differences divided by the standard deviations. In other words, the z-scores for each one of the values for x and y. So if you look at this carefully, we got the mean, we're subtracting each value from the mean, and we're dividing by the standard deviation for that variable. Okay, so this is really basically a z-score. So this is really kind of a measure of how far away from the line that describes the correlation is that particular x value and is that particular y value. And so they're going to multiply each z-score by the one for the other value for that variable, for the other variable for that particular subject. And then we're going to add them all together and divide by the number of degrees of freedom, or just n minus 1, basically. Okay, so, I mean, if you can kind of visualize what's happening here, we're going to transfer that right over to this spreadsheet. Okay, and we're going to work with it now. So first thing I'm going to do is I'm going to need to know the mean for x and the mean for y. We can see those two variables there. Okay, so I'm going to calculate the mean, the average, and obviously these numbers would have to be simple enough for you to work with a calculator, or it would have to be a small enough data set for you to work with a calculator. I'm going to find the average for the y values. Okay, simple as that, right? Nothing new there, nothing that we haven't done before. I'm going to find the standard deviation for x and the standard deviation for y, because we're going to need them as well. Okay, and the standard deviation for y. Okay, so now we got the mean of x, we got standard deviation of x, we got the mean of y, we got the standard deviation of y. Now we're going to actually do a calculation that involves those two values with relation to each individual value of x. So I'll start here. This is going to be equal to the value of x minus the value of the mean of x, x bar. Whoops, put that into the wrong spot there. Click in here, equals x minus the mean of x. Now I'm going to put a $sign in front of the C10 to make sure that it stays, since we're going to repeat that calculation over and over again. I want it to just stay with that mean. Even though I'm going down with the x values, I want it to stay with that mean. And I'm going to divide that whole thing by the standard deviation of x. Now, to make sure it finishes this subtraction before it does the division, I got to put parentheses around here, and I'm going to hit enter. So my value, that value is basically 1.1 standard deviations below where we would expect it to be for this particular situation, and I'm going to copy that formula down. Right? Oops. And I think I did something wrong there. Let's see what I did wrong there. That it didn't successfully copy that down. Do I have the C10? Let me see what I have in here. C5 minus C10. Oops, I know what I did there. I'm guessing that you guys are, you got, thank you, Bill. You're the first guy to notice it. I should have also done that for the standard deviation, since that's not changing either. Okay, $C and $11. Hit enter. Didn't change that value, but now it's going to work better when I fill down. Okay, so I have all those values. So I have all the values that go in here now. Now I'm going to do the same thing for y. Equals the y value minus the mean of the y values divided by the standard deviation. Only thing here is I'm going to put in my parentheses, and I'm going to pin my mean and my standard deviation, so it keeps using the same value over and over again. And again, this not on the test, not like you're going to have to toy with this or worry about this because you'll be using a calculator to do the same thing. Oops. Why did it tell me that? Let's say I'm going to assume that it's wrong and I'm right for the moment. I'm going to fill it down, and those are the values that I wound up with. Okay, let me just check this. D4 minus D10 over, I think I'm okay. Okay, so now I've found the values that I need for the standard deviations for X, standard deviations for Y. So now I multiply one times the other. The X values, X standard deviations times Y standard deviations is equal to this value times this value. Enter, and I'm going to fill that down. Okay, and it asks me to find then the sum of all those values, summation from the first value to the nth value. That happens to be n is 5 here, is equal to the sum of these 5 values. Right, there we go. I got the sum of that. So now all I'm left with, I have this entire part of the formula. So now all I'm left with is multiplying this by 1 over the number of degrees of freedom, or 1 over n minus 1. That's the same thing as saying dividing by n minus 1. So this is going to be equal to this value divided by 4. Am I right there? 4. And I think I made a mistake here somewhere. 4 degrees of freedom. And I definitely made a mistake here somewhere. Let's see, where did I make my mistake? 1 over n minus 1, sum of z times z. Did I have a sign problem here? Okay, up. Did you catch me in another mistake, Bill? Let me try that. No, I got that okay. Right? Didn't I get, oh, you're right. There's a mistake right there. Okay, enter. I'll have to fill this down again. It's a good thing I'm not taking this test. I'm just too, in my old age, I'm just getting too careless. Okay, there we go. This is much better now. Okay, that was just a mathematical error there, obviously. We took the sum of these. Our entire procedure was fine. Okay, everybody relax that we're doing it right. By the way, how did I know that I was wrong when I got the result that I had before? Anybody tell me why I was wrong? How I knew I was wrong? Right? I got a result of, I think, 1.2 or 1.3 or something like that. How did I know I was wrong? Right. It was greater than 1. The R value, Pearson's correlation coefficient, can only be -1 to +1. Closer it is to the absolute value 1, closer it is to -1 or +1, the closer the correlation between the change in X and the change in Y. The closer it is to 0, the less the correlation between the two. So we can't have a value of 1.2. I noticed that in some of the old probability homeworks that that you got fooled every once in a while, made an error on a calculation, and reported a probability as greater than 1. And you can't have a probability greater than 1 because probability of 1 means that you've covered all the possibilities. Same thing here. You can't have an R value greater than 1. As soon as I saw that, I knew I had an error there. Okay, so the correlation here comes up to be 0.90. So in this case, the correlation is positive, which means as X increases, Y increases as well. Okay, and it's a relatively good correlation. Now, you might be asked, presumably on the test, to plot this. Okay, so for instance, if this were 0 and this were 200, oh, excuse me, if this was 0 and let's say 10, 20, 30, 40, and you were asked to plot this, and this were 0 in this direction, and say 100, and say 200, roughly. If you were to plot this, 60, and a value of 60 would be around here, and a value of 12 on the y-axis would be around here. Obviously, I'm not really plotting this, but with a pencil and paper, you should be able to plot this. An x value of 100 would represent a y value of 11, right? Not much change there. An x value of 110 would represent a value of 120. A value of 120 represent a y value of 25. So it's maybe wind up there. And you eventually wind up plotting a straight line. And you can actually draw a straight line that kind of approximates that if you're asked to draw a scatter plot by hand, which wouldn't be hard to do if you have a little bit of graph paper and a pencil and paper and the values that you need. Okay. That's right. Thank you, Sonali. So, is everybody comfortable with that? I'll put this blank version of this back up on Blackboard so at the end of this session, along with a filled-in calculation, so you can take a look at it, so you'll be prepared for tomorrow. But I think you guys have the idea on this. Okay, so that's one of the questions that a couple of people brought up because they think that they were pretty sure that. Professor Yang mentioned that it was likely they were going to be asked to do this. Okay, so next, I just want to go quickly over some of the problems that were in the examples that were given for preparation for the test on Blackboard. Okay, and I have a couple of them open. I have one of them open right here. This is the first of the examples. I have it open this way because I actually have it open in two spots here at the same time. I'm going to move this over. I may not be able to see your questions for a few minutes because I'm gonna need to use more of my screen landscape. So I'm gonna get things out of the way here so I can see both sides of this at the same time. But what you're looking at is the same document, just we're looking at the top of it in one window, and we're looking at the bottom of it where the tables that are referenced in the right window. Okay, so I'm going to go through this quickly. In fact, I'm going to go through it really, really quickly. I'm going to start with the tables. Okay, so let's take a look at these tables and see what they tell us. Um, uh, in these tables, they give us 50. They give us data for 50 states in the United States and the District of Columbia. And in this data, we have for each state, we have the number of murders per 100,000 people. So that's defined as the murder rate, or MR, given the variable MR. The percentage of population with income below the poverty level. This is a percentage, 17%, 20%, 15%. The percentage of population living in a densely populated area, the metropolitan area. For DC, it's 100% because it's all city there. There's no rural area like say in New York, there might be rural areas of Bronx or Brooklyn or Queens or something like that. And the percentage, there's no rural areas like there would be in New York State. Okay, these are states we're talking about. And the variable S for the percentage of families headed by a single parent. Okay, so we have that. They only illustrated here for approximately 10 states, but we have it for all 50 states in the District of Columbia. So we have 51 subjects or states represented. Okay, so now here's a box plot of the murder rates. I'm going to move on from that. I'm just going to go right to the scatter plot. Here's a scatter plot that shows the murder rate versus the poverty rate. The x-axis is the poverty rate, the y-axis is the murder rate. So in this scatter plot, like one you would make up in SPSS, we're displaying the poverty rate on the x-axis and the murder rate on the y-axis. I'm just going to quickly go back here to your questions and ask you which one of these is the independent variable? Is it the poverty rate or the murder rate? Right, poverty rate. The x-axis is the independent variable or the determining variable. The outcome variable or the dependent variable is the murder rate. We're saying that the poverty rate determines what the murder rate is. So if we wrote this as a formula, it would be y, the y-axis, is equal to some function of the x-axis. Murder rate is equal to some function of the poverty rate. Okay, and if we actually go ahead and run a regression, right? A simple linear regression using SPSS, we get this table that's output for our coefficients for our regression equation. Okay, if we draw a line through this, we see that it looks like it slopes upwards, and it looks like a fairly good correlation, right? It's fairly tightly is fairly tight to the line that we would be drawing. This isn't a great scale to view this on. It would look very different if the scale were drawn somewhat differently. Okay, in other words, if this whole thing was 0 to 20, it would be a lot easier to see than 0 to 80, but they weren't able to do that because one of the areas had a very high murder rate, so they had to make the scale from 0 to 80 so you could still see it in this plot. But if it were 0 to 20, if this was 0 here and 20 up here, you'd be able to see this as a pretty good correlation. Okay, now what do we see that's happening with DC here? DC appears to be very different from the rest of the values. So one of the things we might want to consider is whether DC is an outlier, whether there are elements of what's happening with DC that would lead us to exclude it so that we could find so we could determine a little bit easier if there's a significant relation between the poverty rate and the murder rate. Something else seems to be going on in DC than is going on in all these other variables. Well, one of the ways that you can look at this is to simply go ahead and do the regression or the correlation with DC included. And that's exactly what they did here. Okay, so for starters, one of the things you guys may have noticed is that this beta coefficient, this one down here, is the same thing as the R value that you would have gotten if they had put in the model table here. So the correlation here is 0.566, right? It's a positive correlation. As the poverty rate goes up, the murder rate goes up also. Well, 0.566, that's kind of like a mediocre correlation. It's decent correlation, but it's not a great correlation, right? So one of the things we might look at here is, would we be better off if we excluded DC from this correlation? So one of the things we might consider doing is excluding DC and examining the correlation again. And that's exactly what they did next. They excluded DC. And you'll notice something interesting, that if we included DC in this correlation, notice we wound up with a line, this dark line up here, we wound up with a line that if we included DC, because it's all the way over to the right or the left, remember we talked about this kind of like the values that are at the far extremes, like on the left or the right, they have more of an influence on the slope of the line than if it were in the middle. Well, in this case, we can see that actually happening. It's creating a line which, because DC is so much of an outlier, that it's making it a line that is a very poor indicator of the relationship for the rest of the values between murder rate and poverty rate, right? If we see the other, just take a look at the dotted line. The dotted line is the correlation line or the regression line if we exclude DC. And look how much better that fits the bulk of the data. So we're tempted right from the scatter plot to maybe exclude DC. Let's take a look at our numbers here. If I take a look at the R value, again, they didn't bother to put you really should look at the model table here for the R value, but this is going to be the same for a simple linear correlation. It's going to be the same value. 0.629 would have been up there for R. Okay, if you look at this value, well, it's a higher value. It's a better correlation than we had when we included DC. So we have two good arguments for dropping DC. One is that we know that there's no rural area in DC. It's very different geographically than all the other states that we're examining. It's not even really a state, it's a city, really, right? So we got good reason just in terms of what we understand about the geography of DC to exclude it. Number one. Number two, we also can see that that it impacts the regression line that we get, makes it a poorer predictor of the rest of the values, and it also reduces our correlation value, makes it less of a good correlation if we have it in place versus if we exclude it. Okay, so we have a good argument for excluding it. Okay, so let's say we go ahead and exclude it. Okay, so now at this stage, our coefficients give us a what we need. See, under these unstandardized coefficients, B, constant, and the P for the poverty rate. Okay, these give us, these two numbers here give us the values that we need to write a formula which approximates the relationship between the poverty level and the mortality rate. Okay, so I'm gonna write that formula down. Let me see if I can't get my page up here. Okay, and plug in my tablet. Okay, make sure I'm got this right side up. Okay, let's see. And I want some ink. Okay, so if I go back to this, my formula is going to be equal to y is equal to, that's going to be equal to some value, my y-intercept, plus a slope times x. Okay, well, my y-intercept is going to be negative 0.857. Okay, so y is equal to negative 0.857 plus the slope that I'm going to apply to my p-value, my poverty rate, 0.584 times x. Okay, decimal place here and a decimal place here. So now y and x are used just to describe a straight line. The variables that we're really working with here are murder rate and poverty rate. Okay, so in reality, this formula is estimating the murder rate as negative 0.857 plus 0.584 times the poverty rate, the percentage of poverty. Okay, so now if I know that the poverty rate is, say, let's say poverty rate is 20%, right, or 0.20. Okay, my murder rate is going to be equal to, let me see if this will actually work. I'm not feeling too good about this. Let's see. Oops, don't want to do that now. Let's see, 0.584. Oh, yep, says a percentage. Excuse me. It actually uses it as 20 because it's on the table. Just to make sure that you guys understand that I'm not cheating here. Okay, if you go back to how the data was put into SPSS as population was put in as 20. The number 20 represents 20%, not 0.20. So in our formula, we're going to be using 20 instead of 0.20 for P. Okay, so I'm going to go back here. Do I got the right one? Nope. Next one. There we go. Okay, so the murder rate is going to be equal to, for some state where we expect to have a 20% poverty rate, going to be equal to negative 0.857 plus 0.584 times 20. Well, 0.584 times 20, 0.584 times 20 is equal to 11.68. And I am going to subtract negative 0.857. And we would expect the murder rate in that particular state to be, if I got that right, to be about 11 per 100,000 per year. Okay, and let's see what they look like. Let's see if that seems to fit our chart. So a murder rate of about 20%, okay, would represent somewhere in this area here, or about 10 or 11 per 100,000. Okay, so that looks about right. Okay, so now you may take a look at this and you may say to yourself, okay, well, that's very nice that you can use this predictively. So we know the murder rates in all of the states, so would make you kind of wonder, why would you even bother with this? However, there's going to be a lot of situations where perhaps knowing how poverty rate, number one, there may be other situations where it's difficult to measure the variable, the dependent variable, or the y variable. It's difficult to measure it. Easier to measure the independent or predictive variable. So it's valuable to have an equation like that, because you can use that equation to predict the dependent variable, which is much more difficult to measure. In this case, we know them all. In this case, probably a even better use of this would be to examine this and say to yourself, well, gee, the coefficient in front of x here is 0.584. So what that means to me is that for every 1% increase in the poverty rate, I get I get a 0.6 increase per 100,000 in the murder rate. If I have a 10% increase in the poverty rate, I get an increase of 6 people per 100,000 that are murdered, that we predict based on this relationship would be murdered. So you can kind of maybe extrapolate this and help you predict what might occur during periods when the poverty rate goes up, for instance, in extended periods of recession like we've just gone through. Okay, so this might be an important tool in helping you figure that kind of stuff out. Okay, I'm going to pause for a second, see if there's any questions. Any questions, guys, so far? Okay, I'm going to move on to multiple regression. Okay, and the deal with multiple regression is that it's really nice that we can do this for these variables, for the variable poverty rate, and for the variable to determine what the murder rate is. Okay, but there's a lot of other things that may impact the murder rate, the amount of guns that are available in that city, gun laws, and these various other factors that we were looking at. The density of the population, percentage of people living in metropolitan areas. For instance, in New York, that'd probably be higher than it would be for, say, Montana. The percentage of families that are headed by a single parent, that's going to vary from state to state. In DC, it's 22. In Connecticut, it's 10. Okay, per percent. Okay, in Alaska, it's 14, as high as 14%. Kind of surprising, right? In Colorado, it's 12%, and so on and so forth. Okay, we don't have the whole data set here to work with. We only have this one small part of it, but we can see that there's at least three factors that we have available to us that we can examine individually. We could do linear regression and see what kind of effect poverty rate has on murder rate, and we'd probably and we already found a positive correlation. What percentage, what relationship the density of population has on the murder rate, and it's likely we'd find a positive correlation. And the percentage of families headed by a single parent, that would also probably, we would think, have a positive correlation. Okay, I'm guessing because we haven't actually done it. But there could be another dozen factors that we might want to examine as well. We have data for these three factors. So individually, if we were to compare the murder rate to population, that would be a linear regression. Murder rate to the percentage of population in a metropolitan area, the density of population, that would be a linear regression, a simple linear regression. If we would compare the murder rate to just the percentage of families in a single parent household, that would be a linear regression. Now the challenge is, can we get a better predictor of the murder rate if we find a way to combine these three variables, two of these variables or three of these variables? Okay, and that's exactly what they do in these tables. The next time that they look at this, they, instead of just looking at the poverty rate, they repeat the regression calculation. They just move another variable into the box in linear regression, and instead of looking at one variable as the determining or independent variable for the murder rate. Your dependent variable hasn't changed. It's still a murder rate. Okay, this time they're looking at poverty rate and the percentage of people living in a metropolitan area. In other words, the density of the population. Okay, so now instead of having two lines, the constant, our y-intercept, and our slope attributed to the poverty rate, we also have another line, M, for the uh, um, uh, uh, percentage in municipality, living in municipalities, right? So now we have another factor involved. Well, another factor means that we've added a variable to our linear regression. Okay, and in this case, we don't have the R value available to us to look for here. We see our individual coefficient. If we had the model table, we'd be able to see if we improved our predictability, and I'm sure we would have. Okay, but I'm going to go ahead and actually uh, write a formula out for this. Okay, so let me just get a fresh piece of paper. Okay, and I'm going to bring this up a little bit so I can see it. Oops, wrong table. Got jumped ahead there. So you guys are going to see what's going to happen next. So now my multiple regression means that I'm dealing with more than one variable. Doesn't have to be two is more than one variable. It's a multiple regression. So y is going to be equal to our y-intercept plus some value for slope times our percentage of poverty plus some value for slope times our percentage of people in the municipality. If I fill this in, it's going to be negative 7.13 plus 0.6. I'm gonna round this off for now. You shouldn't round off. 0.65 times p and 0.08 times the percentage of people living in a municipality. Okay, and again, I can use this predictively. I can say, okay, well, it's not really y, it's murder rate is equal to negative 7.13 plus 0.65 times p plus 0.08 times m. Okay, I can actually use this predictively. I really meant to put x1, x1 and x2 here. Okay, but I got kind of jumped ahead a little bit. So now I can use this formula the same way that I use the other one. If I know the poverty rate, I know the mortality rate, I can substitute them in here to calculate my predicted mortality rate. Okay, similarly, I'm going to go back here. And once again, they did the same formula, except this time they included I forget what S was. What was S again? Poverty rate, the percentage of people living in a municipality, and the percentage of families that were single parent families. Okay, and again, you got a new slope that's associated with that. So that formula. And let's take a look at the model. They did give you the model for that particular outcome. Okay, and look at this. We went all the way up to a correlation of 0.867 and an R square of 0.75. So using this last model, we improved our predictability to the point where we've accounted for 75% of the variability in the murder rate. We have a pretty good tool for predicting the murder rate in a state if we don't know these what it is, if we know these factors instead of the murder rate. So we have a pretty good predictor at this stage, certainly better than we had with just simple linear regression where we're only looking at one variable at a time. Thanks for the reminder. Okay, let me just write that formula out. Okay, so in this case, oops, the murder rate is going to be equal to negative 17 plus 0.44 p plus 0.06 m plus municipality plus 1.27 times the percentage families in single single parent families. Of these, one of the things you might notice is, gee, this percentage and this percentage seem to have much bigger impact than the percentage of people living in a municipality. In other words, if you increase the poverty rate 1%, or the percentage of single parent families 1%, you get a much bigger impact on the murder rate than if you increase the percentage of people living in single family municipalities in a state, right? You don't get anywhere near as big a jump in the value for murder rate when you look at this equation. Okay, so we can use this predictively. One of the things that you might do with this in order to determine how good a fit you have is you might test it by actually looking up one of the states and substituting the values in this formula for the values that you know, the variables that you know, P, M, S, and then seeing how close you get to the murder rate for that particular municipality. So I'm going to go back up here, and basically what we would do if we were going to test Alaska, we would say the murder rate in Alaska is equal to 17 plus 0.44 times 9.1 plus 0.06 times 41.8 plus 1.27 times the 14.3 the percentage of single parent families. And then I would calculate, well, the murder rate based on these three values, my independent variables, the murder rate based on those values is, let's say, it turns out to be 10. Okay, that's the murder rate we predict from this formula. If I go back here and look at what it actually is when it was measured, it turns out that it's 9. My predicted value is, or my calculated value might have been 10. I'm guessing at that number, so I don't have to calculate it. You can go ahead and calculate it if you want. My actual value is 9. The difference between the number I predict and the actual value is called my residual. Okay, so in this case, my residual would be 1, if that indeed were the real numbers that I got. So you might be asked to calculate a predicted value for one or more of the states, Connecticut, DC, one of the states that you have, and you might be asked to compare it to the actual value and decide what the residuals might be. If you had SPSS available, you guys might remember that we could check off a couple of boxes, and would actually calculate the predicted values and the residual values for all of these uh, uh, different states. Okay, and one of the reasons that we might be interested in doing it is because we would want to make sure that the differences are randomly distributed, that there's no pattern to the differences, that states with lower poverty rates, aren't all underestimated, and so on and so forth, or one end of the graph is underestimated, the other end is overestimated, and so on and so forth. Okay, in other words, we're interested in the way those are distributed as another test for how our system, our formula, our regression is working. Okay, so I think that we didn't actually go through all the questions there. Let me just take a quick spin here, see if there's anything unusual. First question was a chi-square example, and they asked you, it reports chi-square value is, let me just go through this quickly, is 128 based on 9 degrees of freedom. Interpret that. Well, what do we need to know to interpret it, a chi-square value of 128 on a table, a 4x4 table like this? 4x4 table is 9 degrees of freedom because it's 4 minus 1 is 3. Rows is 4 minus 1 is 3. 3 times 3 is 9 degrees of freedom. Okay, what do I have to know to interpret that 128? We have to know what the critical value of chi-square is that we need to reject the null hypothesis for 9 degrees of freedom. Anybody know what that is? That's right, Rebecca. The answer to your question, yes, it's the value that you calculate minus the actual value is the residual. Okay, 16.92. So chi-square is 16.92. A chi-square critical value is 16.92. So a chi-square of 128 exceeds that critical value. So what can you say about your null hypothesis that there's no relationship between attitudes about premarital sex and teenage birth control? Right? You'd say that there is a relationship, right? Reject that null hypothesis and say that there is a relationship. Okay, now they mention in this kind of confusing next question they ask you, well, why do these boxes on the corners? Why are they more important? Why do they have more of an influence on this chi-square calculation than the other boxes? These are your expected values, I guess, right? Oh, this is your observed. They actually put the observed minus expected in here. Okay, and yeah, you could probably figure out right away that these numbers are about to be squared. So if they're big numbers, they're going to be even bigger numbers when you square them, right? And so what happens is that they're going to add more to the chi-square value than any of the other boxes. So just their value alone is going to have a disproportionate influence on what the chi-square value is. The other thing is that they represent the most extreme attitudes, not wrong at all to always wrong, and strongly agree to strongly disagree, right? They're the most extreme values. So you kind of like, even if you looked at it, if you look at it from a chi-square perspective, if you just do a simple chi-square calculation, every box is the same as every other box. But if you look at it from the point of view of these are really ordinal values, right? Then you got to figure that, well, gee, some people have, maybe we want to also consider the fact that some people have a particular, the fact that there's so much divergence, that these are so big in the corners, that it suggests to us that people tend to have strong attitudes one way or another about this, right? There's very little room in the middle, and it seems like there's a lot of stuff like that these days, right? Okay, so and this I'm going to let you guys go through the questions on here so we can move on from this. But I think you have a pretty good idea how to answer these questions based on how we discuss this. In fact, I'm not sure. Maybe the way I described it might be closer to what you might see. So okay, so let's move on to something else. So how are you guys doing? You holding up pretty well under this? I mean, you should be pretty well prepared for this test, right? A lot less material than on a couple of the other tests and stuff like that. So I think you'll find it. I think you can afford to have a little bit more confidence in this test than some of the others. Just to go over homework number 9, should be all graded and stuff like that. Some of you guys struggled a little bit with it, which I was kind of surprised at, because it's not it's not that foreign a concept. I think by this time, I think some of you submitted homeworks on this a while ago, so I got a feeling that maybe by this time we've gone over it enough that you feel a little bit more comfortable with it. Okay, just to go over it quickly, I put together this first problem to help you see this in the abstract, and also so that you could build your own reference table of, if I get confused on a test, how can I make sure that I'm not mixing up the numbers? Okay, and one of the ways is to just actually create a reference table like this. So the risk of illness if you're exposed is going to be A over A plus B, right? Sometimes it's easy to see this in the abstract. Sometimes it's easier to see it in a real practical problem. If you're not exposed, it's going to be C over C plus D. The odds of illness if you're exposed is going to be A over B. The odds of illness if you're not exposed is going to be C over D. Now, the risk ratio, remember risk illness, risk of illness not exposed? Well, a ratio is one divided by the other. So it's A over A plus B. Tell you what, I'm just going to copy it, divided by C over C plus D. Okay, I put parentheses around here. I'm going to do it on this one just to remind you. You're going to have to do it on some others as well. But I may not do it on all the others. I may not do it on this next one, for instance. Okay, odds ratio is going to be the odds if you're exposed is A over B. So the odds ratio is just going to be your exposed over your not exposed. Odds if you're not exposed. Okay, overall prevalence. The overall prevalence is going to be the total number of people that got sick. That's the total number of people that got sick. A number of people got sick and were exposed. C number of people got sick of exposed. Total number of people got sick is A plus C. So the overall prevalence is A plus C over, okay, it's going to be over the total number of people, which is A plus B plus C plus D. Okay, number of degrees of freedom for this analysis. Well, we know that's one, but it's going to be a 2 by 2 table, so it's 2 minus 1, 2 minus 1 is 1 times 1 is going to be 1 degree of freedom. And we know from our chi-square table that the critical value of chi-square is going to be 3.84. Okay, and you can look that up on the table, or you can just simply remember it at this point. I'm sorry, 95% confidence interval? Oh, okay. Let's talk about 95% confidence interval. One of the deals here is that if there's no difference between the risk of being, I'm going to use odds ratio for this explanation. The odds of illness, let's say that the odds of illness is 1 to 3. 1 out of every 4 people, or one for every person that's ill, there's 3 people that are not ill. Let's say that that's the rate at which, I'll put it another way. Let's say that you had 40 people that were exposed. 10 of them became ill, 30 of them didn't become ill. The odds of becoming ill is 1 out of 3, or 1 to 3. Okay. Now let's say the odds of not being exposed. Let's say there were 60 people that were not exposed, and out of the 60 people, 20 got ill, and 60 did not get 80 people rather total. 20 got ill, 60 people did not get ill. So the odds of getting ill if you're not exposed is 20 over 60. That turns out to be 1 to 3 getting ill. One person getting ill out of every 4, or one person ill for every 3 that are not. Okay, so the odds ratio is going to be 1/3 over 1/3. So you would expect, if there's no difference between being exposed and not being exposed, you would expect that your odds ratio is going to be equal to 1, right? Because you'd expect the same rate or the same odds of illness if you're exposed or if you're not exposed. So if you have the same number on top and the same number on the bottom, it's going to be equal to 1. So now it's exactly the same deal with risk, with the relative risk or the risk ratio. You would expect the risk of being ill if you're exposed to be the same as the risk of being ill if you're not exposed. So your risk ratio, you would expect that also to be 1. Okay, problem is that whenever we do this kind of analysis, we wind up in a situation where we'll never wind up with, for instance, even if this were true, that getting ill had nothing to do with the exposure, and we had 40 people that we examined that were exposed at random, and we randomly selected 80 people that were not exposed, and we compared the 2 rates. Well, even if there's no influence, we're never going to get exactly 10 and 30. We might get 11 and 29, or 8 and 32 and 21. And just by chance, it's unlikely that we would get exactly the percentage that's in our sample that is really representing the population. So instead of getting 1, we might get, for instance, 1.3. So now the difficulty is that 1.3 is our point estimate. Remember, that's a point estimate. Does that mean that I'm really at greater risk if I'm exposed, right? Because if that number is above 1, it means you're at greater risk if you're exposed. 30% greater risk if you're exposed. So is that really true, or is that 1.3? Is that really just due to chance that if I had done it again, it would have been zero point 0.8 or zero point 0.9 or 1.1 or so on and so forth? How sure can I be that I'm really greater than one there? That's the reason why you calculate the confidence interval. So, for instance, if the confidence interval here, and that's influenced by the sample size and so on and so forth, if the confidence interval here is point, now remember, we're starting with a point value of 1.3, a point estimate of 1.3. Okay, let's say that the margin of error turns out to be half, right? So our confidence interval is going to be 0.8 to 1 point, not 1 point, let's see, 1.8, right? So now I think my point estimate tells me that the odds ratio is 1.3, greater than 1. But my confidence interval tells me, well, the real entire population, we're 95% sure that in the real entire population, the odds ratio is between zero point 0.8 and 1.8. So even though my point estimate is 1.3, greater than 1, I'm not 95% sure that it can't be 1. It can be 1 because we're 95, we're thinking it's between zero point 0.8 and 1.8. Uh, I can only be sure that that it's different than less than zero point 0.8 and greater than 1.8, right? I can't say that it's different than any value in this range. So I would fail to reject the null hypothesis if that were my confidence interval for this value 1.3. Now, had this been instead a margin of error of 0.2, where this came out to be 1.1 and this came out to be 1.5, right? Well, now not only do I have a point estimate of 1.3, but I'm 95% certain that uh, um, uh, uh, the true population odds ratio for exposed and not exposed is 1.1 to 1.5. In other words, I'm 95% sure it's in this range. So I'm also 95% sure it's different than 1. Okay, so to make a long story short, too late, right? A little late for making that long story short. Two, one, but I want to make sure of this because I still got a few people that are still struggling with this a little bit. So to make a long story short, Um, if this is your confidence interval for the odds ratio, you fail to reject the null hypothesis because it includes 1. If this is your confidence interval for the 95% confidence interval for the odds ratio, then you can reject your null hypothesis because the odds ratio, you can say then that the odds ratio is different than 1. It could also both be lower, right? It could be 0.08, 0.05 to 0.08, so that all the values are under 1. As long as it excludes 1, you can reject your null hypothesis. Okay, so what is your null hypothesis in this case? Well, your null hypothesis could be the relative risk is equal to 1. No difference in risk exposed or unexposed. Your odds ratio is equal to 1. Or your null hypothesis could be that there's no relationship between between exposure and between exposure and illness. Most likely, you would probably use one of these two because it's just simpler. And you could, like everything else, you could say that your alternative hypothesis is the relative risk does not equal 1, or your relative risk is greater than 1, or something of that nature. Okay, so you could play around a little bit. Okay, I got a can't hear you. I hope I'm back again, right, Leslie? You can hear me now. Can you guys hear me? Okay, good. Thank you. Okay, good. All right, excellent. All right, so just to move on from this, in this case, you got a specific example of this that you could calculate. In other words, you were asked to fill out this table. You had 100 people that didn't eat the tuna surprise, 100 people that ate the tuna surprise that didn't eat the tuna surprise. I got that backwards. Okay, and out of 100 people who ate the tuna surprise, 63 became ill. At 100 that didn't, 24 became ill. So this would wind up being 63. This would wind up being 24. Of course, 100 people, you would know that this is going to be 37. and this is going to be 76, I guess, right? Yes. And the totals, and this would be 87 and 113. Then you could calculate your expected values. Now, just quickly, how do we calculate our expected values? Right? First thing we need to know is we need to know the overall prevalence for the um, for this particular illness. Out of all the people, what percentage got ill? Okay, so now 87 people out of 200 got ill. If you don't remember that, you can always go back here and see what's the overall prevalence. Well, it's A plus C. It's this box divided by A plus B plus C plus D. If you don't remember that. So if we go over here, sure enough, it's 87 over 200. So our prevalence is equal to 87 over 200, or in other words, zero point 0.3. Let's see, 90 would be 80. 90 would be 45. No, 45%. Uh, 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 um, 2, 4, 40, 43.435. Okay, 0.435, 43.5%. Okay, so thank you for the help there. I glanced over too late there to see it, so I wound up figuring it out for myself. So now, to determine the number of people that belong in this box, right, we would say, well, we would expect everybody, if there's no difference between eating the tuna surprise and skipping the tuna surprise, we would expect everybody to get ill at the rate of 43.5%. So that would mean we would expect 100 times 43% is going to be 43.5 people in here, and 100, same rate here for skipped it, 43.5 here. If this were a different number like 200, you just multiply by 43.5 to get the right number that goes in here. As it happens, it's the same number. The difference goes in here, 56.5, right? Yes, I think so. 56.5. And those are my expected values. And then you would calculate chi-square values and compare it to your critical value chi-square and so on and so forth. And in this particular problem, you wound up doing a simple linear regression similar to what we already reviewed in the example problem that had been uploaded to Blackboard. And you would take a look at this and you'd see, you'd use the output from SPSS. So it's a good idea maybe to print out a copy of the output from SPSS for the model for the for a simple linear regression, the coefficients, and for multiple regression, the coefficients, like, or you could just take the one you already have that we just went over, and make notes on it so you can remember how to build a formula, how to calculate the predicted value, how to calculate the residual value, and so on and so forth. Then bring those into the test with you. Hang on to them and bring them along so that if you're under a lot of duress during the test, that you don't have to worry about kind of forgetting, where to look for this stuff. Relatively simple stuff, but I understand it. Like, this is your first look at it, and in for some of you guys, 20 years since you might have taken a math course, or maybe first ever if you hadn't taken a statistics course before. Okay, the 95% confidence interval for these proportions is going to be a little bit complicated. I doubt that you're going to be asked to calculate the confidence interval for odds ratio or relative risk, because it's really a combination of two proportions. I think it's more likely that you would be given it, or you would be given a table like an output from SPSS where you would be able to see it. Okay, let me end up by putting out by showing you such a table. Let me see if I got something I can do a regression with. I think stenosis was one, right? I'll calculate the odds ratio, relative risk, and then we'll figure out we'll see where the confidence interval is hidden. I don't remember. Kadena is asking, if the residual value is the observed values minus the expected, or the expected minus the observed. Be honest with you, I don't remember. I don't think it makes that much difference. I don't recall which one it is. We could ask us. I could ask SPSS to figure it out for us, and maybe we'll see what they say. Let me just see here. Okay, here we go. Analyze, and now I am going to do a crosstabs. I'm going to compare gender in the rows, my exposure, and stenosis as my columns, my outcome. And I'm going to say I want you to calculate. I want you to show me observed, expected, percentages by rows, and I want you to calculate the chi-square and the risks. Okay, let's see what all these tables look like. Here we go. Here's our tables. And if I look here, my Pearson's chi-square is is about 8, 1 degree of freedom. We're going to wind up, and our p-value is 0.005, less than 0.05, so we know we're going to reject. If I look down here for odds ratio, for gender, female versus male, okay, what that tells us, 39% of females had, in this elderly population, had aortic stenosis. 58% of males. So the relative risk is 39 over almost 60, 40% over 60% roughly, which is about 2/3, and which is about, am I right about that? Is about 2/3. So if I look at the second row here, second row cohort presence of aortic stenosis, 0.67 to 2/3. That's my relative risk. My odds ratio, 43 over 66 divided by 62 over 44 is 0.462. If you actually do that division, 43 divided by 66 divided by 62 over 44, you'll get 0.462 if you want to confirm that that's your odds ratio. Both of those numbers are less than 1. Those are our point estimates for odds ratio and relative risk. Okay, both of them are less than 1, but we don't know if we can reject our null hypothesis yet until we look at what our 95% confidence interval, and here it is given to us right here. That's our point estimate for odds ratio. Our confidence interval is 0.27 to 0.80, right? And that excludes the number 1. So we're 95% sure that the odds ratio is less than 1 or different than 1. So we can reject our null hypothesis that the odds for males and females is the same. And you'll get the same result for relative risk, 0.5 to 0.9, and you'll get the same result for chi-square, less than 0.05. All of these will tell you the same thing, to reject the null hypothesis. Okay, but that's where you'd wind up finding. You might get a table like this shown up on your test. I don't think he'd ask you to calculate it, given the tools that you have during the test. Actual predictive values. Let's see. I can post some of the stuff that I just did here. Let me see if I can't find another file quickly, just to show you the regression, and we'll calculate that. Row 95. I think we could do that. Okay, and literacy, I forget what we used here. I'm going to do a linear regression, and I'm going to choose average female life expectancy, and I'll see how let's see, literacy rate affects that. Now, I'm also going to ask it to calculate the predicted values based on the formula it generates and the residual values. So when I go ahead and do that calculation, our output tells us that that's a really good correlation. 75% of life expectancy for females is determined by the literacy rate, or it could be predicted by the literacy rate. The variability, and it could be predicted by literacy rates. Good, significant result, so on and so forth. And when I go back to the data file, it adds some values. It tells me that the predicted value for this first group is 50.2. That's the life expectancy we would expect for that first country. The actual female life expectancy was, I don't know which one it was. Which one did I use? Well, 44, 45. It's one of those. It's lower. Let's see. Let's see if the difference between the predicted value of 50 and the actual value of 40, if it's positive or negative. Turns out to be negative. So it uses the predicted value minus the observed value, the actual value, to calculate the residual, if that answers that question. So I would do the same thing that SPSS does. I'd use the same sign. Okay, guys, I think